Okay, I'm going to give a couple of worked examples of rather more involved so-called practical single variable optimization problems using discovering critical points and applying the second derivative test. So the two particular areas, one is in the arena of PC games, and the other is an application in the field of medicine. So the particular PC game is something called the League of Legends. And in this game, one is given particular health score, denoted by H, a certain quantity of armor, denoted by A, and one has some initial number of tokens to spend. If one wishes to purchase additional armor, then one can do so at a cost of 18 tokens per item. And if one wishes to improve one's overall health, one can purchase additional health benefits at the cost of 2.5 tokens. What one wants to know is how should one spend one's tokens in order to maximize effective health, and effective health is defined by that function. It is the amount of health score one has multiplied by 100 plus the total amount of armor, and that whole thing is divided by 100. So it's a maximization problem, an optimization problem. So how do we go about analyzing that particular optimization problem? Well, the first thing to notice is suppose we spend X tokens for some value of X on improved health. Then we started with T tokens, improved health tokens cost 2.5 units, and armor tokens cost 18 units. And that means if we spend X units on improved health, we have remaining the number we started with minus 2.5 times X divided by 18, the cost of armor, to spend on additional units of armor. So what we want to find in terms of the number of improved health tokens we buy is we want to maximize the effective health that we have, and that turns out to be the amount of money, the number of tokens we spend on health multiplied by that term inside the brackets, and if we simplify that, we get the expression on the extreme right of the bottom line. So, going on, for that function, we wish to maximize that function, find the value of x that maximizes that function. So we've got to examine its critical points. We have to find its first derivative. First derivative is a fairly straightforward function, and the first derivative of the effective health function, that turns out to be 1800 plus the number of tokens we started with minus 5 times the number of tokens we're going to spend on health units, and that whole thing's divided by 1800. We need to find critical points of value of x that will make that equal to 0. And the critical point It's just simply when x is equal to 360 plus the number of tokens we started with divided by 5. And that is a maximum, and to confirm it's a maximum, let's look at the second derivative. Second derivative is just a constant. More importantly, it is a constant value which is negative. So the value we've identified, the critical point we've identified, is indeed a maximum. And moving on, this is quite an interesting application of optimization, and it concerns an issue that arises when intravenous injections of some medication are injected, are given, and how effective those are. So we have the amount, the dosage that we wish to administer. And depending on factors like the substance being used, the patient weight, metabolism, other things, that will be absorbed at a particular rate, denoted by alpha. However, it will also, some of the dosage will be lost through actions such as breathing, perspiration, all sorts of other bodily functions, and the elimination rate is denoted by beta. So as the dose is being administered, we're having this constant trade-off between how much is being absorbed and how much is being lost, eliminated. And what we're interested in is what's the optimal length of time to administer the injection that will maximize the concentration of the dosage. If we leave it too long, then elimination will wipe out most of the benefits. If we leave it too short, perhaps the correct amount will not be absorbed within the time we allow. Now, a study has shown that the dosage concentration can be estimated by that function. Now, D, beta, and alpha, those are all constant values. So the important thing governing how to optimize concentration is that second term inside brackets, the 1 divided by exponential alpha t minus 1 divided by exponential beta times t. So, just to refresh, the dosage amount being administered, the absorption rate, and the elimination rate, those are all constant values. They do not depend on the time the dose is being administered for. So let's have a look at that function. Noting that d, alpha, and beta are all constants, we find that the first derivative of that function with respect to t, well, the constant multiplier isn't going to change. It's the term inside the second collection of brackets. And when we differentiate the exponential functions that are involved, so in effect it's exponential minus alpha t exponential minus beta t. When we find the first derivative of that, then we get minus alpha and plus beta respectively. The critical point, if there is one, will be at the value t. If we concentrate on the term inside the brackets, it'll be at the value t where beta multiplied by exponential alpha t minus alpha times e to the beta times t, it will be when that equals 0. So let's do some playing about with that, and what we find suppose we just rearrange the sides and then take logarithms of the quantities on both sides. So we take the natural logarithm of beta multiplied by x alpha t. Well, logarithm of a product, we just add up the sums of the logarithms. So we get logarithm of beta, natural logarithm of x alpha t. Well, that's just the exponent value. We get a similar thing with the right-hand side. So we are looking for the value t with a logarithm of beta plus alpha multiplied by t is equal to the logarithm of alpha plus beta multiplied by t. And that turns out to be value t, which will maximize the effective concentration of the dosage log beta minus log alpha divided by beta minus alpha. So log of the elimination rate minus log of the absorption rate divided by the elimination rate minus the absorption rate.